In the first video on this series on diodes, we looked at a perfect device. Let's now see what a real semiconductor diode looks like. Let's start with forward bias. As we increase the voltage across the diode, at first nothing happens. This is because conduction has been blocked by the depletion layer. Finally, when there is enough voltage across the diode, current begins to flow. This voltage is between 0.5 and about 0.8 volts for a silicon diode, but is different for other types. The current through the device then increases exponentially. The equation for this current is shown on the screen. Notice how the conduction through the diode, and through semiconductor devices in general, does not obey Ohm's law. Ohm's law only applies to simple materials. This is because the mechanism of conduction in these simple materials is different from those in complex devices like semiconductors. You can study this in your own time. In reverse bias, a very small current due to minority carriers does flow. This varies depending on the type of diode. Eventually, usually at a reverse bias of a few hundred volts, the diode breaks down. This is called reverse breakdown. This normally destroys a diode, although as we'll see later, some diode types, particularly the linear diode, are designed to exploit it and not be destroyed. So the diagram on the screen summarizes the effects at different voltages. The bulb will remain off until we reach 0.5 to 0.8 of a volt, and then it will switch on. In an actual circuit, we'd put a resistor in to limit the current. Note, however, that when the diode is on in normal conduction, it always has the voltage of 0.5 to 0.8 of a volt across it. This voltage is necessary to overcome the depletion layer, and so we lose this voltage, and it's called the diode drop. In reverse bias, essentially no current flows until the diode breaks down.